My name is Yushan Liu. I am a PhD student from Princeton University. Today, I'd like to give you a talk on my paper entitled Towards a Timely Causality Analysis for Enterprise Security. This is collaborative work with Mu Zhang, Ding Li, Ken Kuji, Zhichun Li, Zhen Yuwu, Chang Zhen Ri, and also Pritik Mito. Here is the outline of my talk today. First, we'll start with a brief introduction. As have mentioned by speakers before me, advanced persistent threats, APT in short, have become a serious challenge for many enterprises. In the past decade, over 6,000 severe incidents have been reported, including big companies like Home Depot and Target. And this has caused significant financial losses and also reputational damage. APTs are stealthy and hard to capture because they are often conducted in multiple stages. Here is an example of an APT attack information insider data theft. You can see that we have this attacker here who first downloaded a malicious script and also executed this script on a high-profile host to steal some confidential or sensitive files, for example, like intellectual property-related files. Later, he transferred these files to a low-profile host in order to keep his traces undetected and below the radar of detection systems. Finally, he moves these files to his own site. So in this process, detection systems can raise alert at one of these stages. For example, antivirus programs can capture the malware dropped on the target system. In our case, the firewall monitoring the incoming traffic can reveal a suspicious packet and thus identify the first step in this attack. However, intrusion itself is not enough. It can only reveal a very small portion of attack traces, and a large portion of rest individual footprints, they can seem quite innocent, insignificant, and thus they can keep undetected. To achieve a thorough and sound understanding of the attack, analysts have to detect all the attack traces, including uncovering the provenances and also diagnosing the consequences. So they perform attack causality analysis to connect the dots. The way to do this is, of course, to use audio logs to reconstruct multi-hop causal dependencies between system objects, including files, processes, and also sockets. We support cross-host tracking by using reverse IP mapping here. So in our example, we start tracking from the detection point so we can identify the sequence of steps in this attack. We first trace a socket event, followed by process creation, file read and write, and finally we end with a socket event. So in this way, we finally construct a forward tracking graph. Ideally, our forward tracking graph should only contain the attack events. However, in practice, the truth is oftentimes, a large amount of noises are incurred by system routines, shared files, and also long-running processes. In our example here, upon login, SSH will automatically trigger a set of Linux utilities in order to update the messages for user interaction. So these processes further fork their child processes and create a cascading effect on our forward tracking graph. So analysts will consequently spend a lot of time investigating these normal activities, but this is certainly undesirable because attack causality analysis is a time-sensitive mission due to two reasons. First, if the causality analysis is really slow, the system downtime will be increased because we want some complete cleanup before we can safely return to normal operations. And as a result, financial losses can grow to millions of dollars. The other reason is that slow causality analysis can cost us a chance to prevent feature attacks. Intrusion may further develop and cause more damage, and if we cannot take prompt responses and understand the attacker's intentions, we may be unable to prevent feature damage. So all of this motivates the study of timely causality analysis. However, the time aspect has been largely overlooked by previous works. They mainly focus on studying addressing the graph explosion problem using data reduction. So they eliminate irrelevant events. However, the result is they still invest a lot of time looking at relevant yet benign and normal system routines. Essentially, this is because they don't have the ability to distinguish abnormal activities from common system activities. As a result, they have no choice but to treat all dependencies either abnormal or normal equally and keep track of every relation in the forward tracking graph. Our solution to accelerate the attack causality analysis is to prioritize the search for abnormal activities. We do so to the best of our knowledge. We are the first to introduce the notion of priority to the graph construction phase. Here is an overview of our system. Our PRIOTRACKER is actually built upon a very large monitoring platform. At the very bottom here, you see that we have agents running on 150 hosts, including 54 Linux machines and 96 Windows machines. They are running daily in an enterprise used by researchers, product developers, and also system administrators. These agents collect OS-level events, and these events are later stored in a database. We have a dataset of terabytes of millions of events collected in 1 week from these hosts. And this is the largest dataset we know from previous work. And also, this large dataset gives us a centralized view of the entire enterprise. And this can also facilitate analysis for cross-host tracking. On top of this system, we built our PRIOTRACKER, which consists of 2 components. The first one is a reference model. The second is a causality tracker. I will give you more details into the reference model. The basic goal of this model is to record the common system routines from homogeneous pure systems in a corporate system. Here we have like a set of homogeneous hosts. And our intuition is that if an event has been observed frequently from the majority of these systems, of these hosts, we will tend to believe that it is normal. And if an event is rarely seen from most of the hosts, we treat it as more abnormal. So we do this by counting the occurrences of an event on different machines, and we output a rareness score based on that. Our reference model have 2 design goals. The first one is we want to ensure that it is general, because OS events carrying the same semantics can be very diverse cross-host or over time. Our way to do this is we perform event abstraction. We represent each process by its executable path and also file by its path name, and also socket by the IP address and port number. We also normalize the path for different user accounts. We use some directory services to replace the usernames by the same wildcard. Another issue we want to look at here is the robustness of our model against poisoning attacks. The attacker may compromise several machines in the enterprise and then create a burst of recurring malicious events. In this way, it can trick our reference model into believing that their event is normal, which actually is not. Our way to mitigate the effect of poisoning attacks is to introduce a time window here. We assume that, for example, we can set the time window to be 1 week because we assume that the enterprise operates on a weekly basis. So in each time window, the repeated occurrences of the same event on the same host will only be counted once. In this way, a spike of recurring malicious events only have limited power, and we actually raise a bar for performing poisoning attacks. Now we have the rareness score for each event. We are ready to perform priority-based causality tracking. The naive approach that comes up to mind, of course, is to simply select the most uncommon event at each step. The problem is that it doesn't fix the issue that deeply buried attack traces can also be missed before an analysis deadline. This is because the rareness score only reflects the property of a single event, and it will lead us to be stuck at some local optimal. So we formalize this problem as a global optimization one. We set our goal as to find the maximum number of unusual events within a time limit. We do so by considering a set of factors. Aside from rareness score we have talked about, which reflect the local rareness, we also consider some other topological characteristics of this event in the causality graph. For example, fan-out score. We quickly exploring low fan-out events to expand the search area and avoid being stuck at some local optimal. Our methods can also incorporate other factors. So finally, we get this priority score, we assign it to each event, and we select the event bearing the highest priority at each step. The priority score is computed as a linear combination of rareness score and fan-out score. So this actually demonstrates a trade-off between analysis coverage and time effectiveness. And we need to strike a really good balance here. We do so by learning the weights using hill climbing algorithm. Finally, I will show you the evaluation results of our PRIOTRACKER. Here is the setup. As I mentioned before, we run on 150 hosts. We have this training set to learn weights for our priority function, which contains over 1,000 random starting points that will give us big graphs. We also have the test data set that is over terabytes of data sets collecting OS events from 1 week. And the time limit is set to 1 day. We reproduce 8 representative attack cases used in previous work, except that we also consider noises interleaved with normal system activities. We evaluate the performance of our PRIOTRACKER in terms of 2 metrics. First, of course, accuracy by calculating the false negative rate. You can see from the table here that for 2 attack cases, the baseline approach can only actually misses 60 and 40% of attack traces, while our PRIOTRACKER is able to capture them all. Also, we consider time effectiveness. You can see from the result here that baseline approach failed to capture all the attack traces before the deadline, that is 1 day. But our approach only takes about 40 minutes and 6 minutes to find them all. So we actually speed up the analysis process by up to 2 orders of magnitude. Let's revisit our example here. You can see that to reach the final step in the attack, our PRIOTRACKER only takes about 30 steps, but for the baseline, it takes over 200 steps. This is because they investigate the normal activity that spend a lot of time there. So our approach is able to prioritize the search for abnormal activities over the Linux routine maintenance. Okay, finally, I can conclude my work here. We are the first to formalize timely causality analysis and to introduce the notion of priority to a graph construction. We implemented the system named PRIOTRACKER, and also we built a reference model to enable us to distinguish abnormal activities. And also, we evaluate on the largest data set. Our results show that we can capture the missing parts by existing trackers and also speed up the analysis process. Okay, here is all. Thank you very much for your time. Do you have any questions?
Yan Chen from Northwestern. Again, very interesting work. I wonder, since you care about time so much, and it looks like you're essentially doing the anomaly-based detection, have you thought about if this can be applied for real-time detection instead of doing forensic analysis?
Real-time detection.
Right. So you want to catch the attack while it's happening instead of waiting for just doing the forensics.
Yes, I think yeah, our reference model that is used to detect the normal activities can actually be used to some real-time detection because we sort of use some cross-sourcing methods to distill the abnormal ones from normal ones. Yeah, I think this approach can be applied to detection part.
What kind of
sorry?
Go ahead.
But causality analysis in nature is a postmodern fashion, so it's really hard to apply it in like online fashion.
Right. So that's what my question. Like, what kind of match would you need to do in the real time?
Sorry, could you repeat the question?
I mean, if you want to do a real time, what kind of matcher would you need to do it?
To do the causality analysis real time.
No, to do the real time detection, you need some matcher to match their. To compare with the flying traffic and to match, okay, well, at this point you detect it.
I think.
Yeah, we can take our time.
Yeah.
I'll jump in, and I have the exact same sort of comment. I think that this is a really interesting idea, this optimizing query time for forensic analysis. It does seem like you're striking at the rareness is a measure of, this is an anomaly in the system. And so I guess, along those lines, I was wondering if you attempted to set sort of like a threshold for rareness and see are there ever any benign events that show up as being exceptionally rare, or does that end up being a good measure for malicious behavior in your data set?
Yes, we have set different values of threshold to see, and also we also explore the distribution of this rareness score across different events. Actually, we have a table in our paper that actually shows that most of the ages in the attack traces are considered very rare in our reference model.
Cool, thanks.
Okay, I think this question might be actually quite similar. Frankly, UC Berkeley. So yeah, your priority score has an alpha and beta weights for the rareness and the fan out. And you said you said it was an optimization problem. Can you kind of expand on what exactly you're optimizing? Do you need to have real attacks that you're trying to optimize catching all of those attack edges? And does this differ between different organizations? Just basically, what are you actually optimizing for?
We are trying. Assume that we have a tracking algorithm here, and we have a time limit. So within this time limit, in using this tracking algorithm, we will have the number of real events that can be captured within this time limit. So we are trying to optimize the amount of real events here. Ideally, we should maximize the number of attack edges. That is our primary goal. But the fact is, the attack can have a huge degree of variety, and we don't really have the numerous attacks. So our alternative will be to find the more seemingly abnormal ones within the time limit.
Okay, thank you.
Let's thank our speaker.